Okay, we're looking at relative rates of growth today. So we're going to compare two functions and decide which function is growing at a faster rate. So first of all, we're going to look at two functions f and g. Just notice here that switch these around. So just in the chart, they are switched. So fill in the chart for f of x equals 2 to the x. Then when x is 1, that has a value of 2. When x is 2, that's 4. When x is 4, that's 16. When x is 10, that is 256. No, 1024. Okay, so x is getting bigger. And so the value of f is getting bigger. In g of x, x is getting bigger as well. That's going to be 1. 2 squared is 4. 4 squared is 16. Those happen to be the same. And then 10 squared is 100. So then if you did something bigger, as x goes to infinity, that f of x, which is equal to 2 to the x, is going to be getting a lot bigger than squaring. Okay, so it's pretty clear that f of x grows faster than g of x. So I'm going to put in the function just in case you forget to change them up top. Okay, so it's pretty clear that that occurs based on our examples. That's kind of like inductive reasoning. Then let's look at graphically. So if we have here, if f grows faster than g, so this would be f and this would be g. Okay, then when you take the limit as x goes to infinity of the ratio of those, f over g, this is going to end up being a much bigger number. So that approaches infinity, okay, when you take the limit of the ratio of those functions. If f grows, so in this case, if f is the bottom function and this is the top, then this one is going to be big compared to the numerator. So as the denominator gets big, the whole value of that ratio as x goes to infinity is 0. Okay, so that's going to help you decide when you're comparing functions, which is growing faster. Take a look at the next example. Now f of x is 2x and g of x is x. X going to infinity, which one grows faster? So substitute the values in. So that's 2, that's 20. Now we're going to bigger x values. That would be 200. That would be 2,000. Then when x is 1, so that would be 1, 10, 100, 1,000. Okay, so in this case, when you compare these, you can tell. If you take the ratio of f over g, you get 2, right? Here you get 2. Here you get 2. Here you get 2. So since f of x is always twice as large as g of x, both functions grow at the same rate. So if you actually get a limit that's not 0 and not infinity, then they grow at the same rate. Okay? That's how they would look like. That particular example would be here. This would be f, this would be g. Okay? But that ratio of the y values for any x is always going to be, in this case, twice as much. Okay? And it kind of looks like that if you drew a vertical line. And, oh, not like that. Let's do that. So if you drew a vertical line there, it's cutting that in, this part is in half basically, so this is twice as much as this. Okay, so let's take a look at the next page. So now we're going to actually compare the rates of growth for the following functions. So let's take limit of the ratio. So limit as x goes to infinity. Let's do ln of x over x. Okay, so that goes, when we look at x going to infinity, we get infinity over infinity. Okay, which you would use L'Hopital's rule. So limit x goes to infinity of 1 over x over 1. okay, which is just limit x goes to infinity of 1 over x, which we know that equals 0. Okay, so if that ratio gives you, when you take the limit of that ratio and you get 0, that means the denominator grows faster because that denominator is getting bigger compared to the numerator. So in this case, therefore, g of x equals x grows faster than f of x ln x. Okay. Same with the next one. So we'll do limit x goes to infinity of ln x over x squared. Okay, and then same, I would use L'Hopital's rule because it's infinity over infinity. Oops, that's infinity, sorry. Okay, so simplifying that. And then obviously if the numerator is 1, the denominator is going to, x is going to be infinity in the denominator. That's going to be much greater, so that's going to be 0. Okay, so again, same thing. Now your g of x was in the denominator, so g of x grows faster than f of x. Next one, I always have to think about, okay, what do I want in the numerator or what do I want in the denominator? I would probably look at, if there's 2 terms like g here, put that in the numerator. Maybe you can split it up into 2 terms. So sort of the more complicated function, you might try to put that in the numerator. Okay, and so really now I can show that as 1 plus sine of x over x. Okay. So now if you're thinking what happens here as x goes to infinity, well, think about sine of x. Sine of x is going to be less than or equal to 1, greater than or equal to negative 1. It's never going to be bigger than that. And then if x is going to infinity, then basically this is going to approach 0. So this is kind of like the one we did yesterday with cos of x over x. We used the squeeze theorem. So kind of the same here, right? And so this equals 0. So by the squeeze, then this equals 0. So that means sine of x over x equals 0. This is different from the limit of sine x over x, where x approaches 0 that you did back in Math 31. That's probably on the formula sheet, and that equals 1. So this is different because x is going to infinity. So this is going to be just equal to 1. So now it does equal a value. So if you get a limit that's not 0, then it means they both grow at the same rate. Okay, so that is not equal to 0 and not infinity. Okay. Next one, same thing, find the ratio. What one do you want to put in the numerator? It doesn't really matter. They're both exponents, right, and both powers. So once you show it like that, you could actually show this as e over 2 to the x. Okay? Now, if e over 2 is greater than 1, then raising it to x, where x goes to infinity, it's going to go to infinity. Okay? If e over 2 is less than 1, then it's going to approach 0. So e is 2.71. Let me just put it in there. I won't forget exactly. So e 2.718. Yep. So e So obviously it's going to be bigger than 1. Oops, sorry. So e over 2 is greater than 1. So therefore, I'll put it over here. Actually, I don't have to write out the whole thing. Okay, so that limit goes to infinity, so that means the numerator grows faster than the denominator. So f of x grows faster than g of x. Okay. Next one, again, I like to I'm going to put the more complicated one in the numerator. So then when I can split this up, that's going to be 1 over 3 plus 5 over 3x. Okay, and then 5 over 3x is going to approach 0. So this is going to end up being 1/3. Okay, 1/3 is not 0 and not infinity. So therefore, f of x grows at the same rate as g of x. Next one, they're both logs, different bases. Okay. So this goes to infinity, so does this. So maybe use L'Hopital's. I guess you could use change of base if you wanted to, but I'll just use L'Hopital's. So the numerator will become 1 over ln b times x, which I'm going to put. So 1 over x times ln b, and then the denominator is just 1 over x. So invert and multiply. That's really, so these actually divide out, right? So that's going to be 1 over ln b, which is a value. It's a constant, right? So this is constant. That's not an x there. So this is not equal to 1. That's right, not equal to 0, not equal to infinity. So therefore grow at the same rate. Okay. All right, next one. All right, so definitely more complicated. I don't know, it doesn't really matter here. You're not going to be able to simplify right away, so I'll put the radical and more complicated up top. 3x squared minus log these 2 of x in the denominator. Okay, so this is going to end up going to infinity. So remember back to Math 31, what you can do, these actually basically have the same degree. That's 3x squared in the denominator. Well, the root of x to the 4th is x squared. So what you could do, you could take the derivative, but think about that. That's going to be kind of messy if you do use L'Hopital's rule. So I would go multiply by 1 over x to the 4th square rooted, which is equivalent to 1 over x squared. So if I do this over this, I'm not changing anything. I'm basically multiplying by 1. They are equivalent. So then I'm going to have 1 minus 2 over x cubed plus 5 ln x over x to the 4th. over 3 minus log base 2 of x over x squared. And then, taking a look here, as x goes to infinity, this is going to go to 0. X to the 4th is going to grow much faster than ln x. Did we do one like that? We did in 3b. We found that g of x, the x squared, grew faster than ln x, so obviously x to the 4th will grow faster. And then same thing here. X squared is always going to grow faster than a logarithmic function. So this is going to end up being the root of 1 over 3, which is 1/3. Okay, so that's not equal to 0, not equal to infinity. So therefore, they're going to grow at the same rate. Okay. Oops, what happened? Did I miss something? Give me a sec. Okay, last question. So, our property anyway, and then a question. If f grows at the same rate as g, as x goes to infinity, and g grows at the same rate as h, as x goes to infinity, then f has to grow at the same rate as h as well. Okay, so it's the transitivity of growing rates. So transitive property. So sometimes you might want to use this because maybe you have a function, like an easy function that you can compare both to without doing the limit of the ratio of both of them. So for example, f of x, root of x squared plus 5, g of x, show that they grow at the same rate. Now you can just do the ratio of them, okay? Or you could compare it to something easy, like x. So let's compare, oops. So we're going to compare each to another function. Let's call it h of x. Okay. So now the limit of f of x over h of x. Okay, what happens there? That's pretty easy to do. Multiply by 1 over x squared square rooted, which is the same as 1 over x. Or you can take the derivative, use L'Hopital's and take the derivative. But this ends up giving you, this is actually a bit faster, right? Okay, so that's going to end up giving, that goes to 0. So root of 1 over 1, which is 1. Okay, so you know those grow at the same rate. Then compare your g of x. So limit of g of x, g of x, which is 2 root x minus 1 squared to that h of x. And in this case, you could expand out. So that would be 2x minus 4 root x plus 1 over x. And then again, you're really multiplying top and bottom by 1 over x. We get 2 minus 4 over root x plus 1 over x all over 1. Okay, so then those go to 0. So we get 2. Okay, it's a different limit. But, so this is not equal to 0, not infinity, so therefore same rate. Same thing here, not equal to 0, not equal to infinity, so same rate. Okay, so since you're comparing both of them to h of x, that must mean because both f and g are compared to 8, then
all students, stand. Just a reminder, have your station. If you're wearing green, coming down the hallway, the main hallway, by the big gym, blacksmith is gonna be there, the flex will be the gym,
That's it.
walk your